and welcome to our lesson on binomial expansion. So we're going to start by looking at something called Pascal's triangle. This is a blank version of the triangle, and there are just tons of patterns associated with Pascal's triangle, but one of them is useful in the process of expanding binomials. That is, finding something like let's say a plus b to the sixth power without actually having to perform the multiplication. Okay, so let's look at this triangle. If you've not seen it before, basically Pascal's triangle starts out in the top of this triangle with a 1 in what we would call the first row. In the second row, it also has a couple of 1s. And then at the beginning and end of each row, we'll start and end with a 1. And to find the other numbers, or all the other numbers, we're going to be adding up the two numbers above the spot we're in. So again, every row is going to start and end with a 1. And if I wanted to find this spot here, what I want to do is add the two that are above it. So if I add the 1 and the 1, that's going to give me a 2 for this location. Going down to the next row, again, I'm going to start with a 1. If I add 1 and 2, then this result should be a 3. Again, adding the 1 and the 2 here means this result should be a 3. And then again, I'm going to add or end with a 1. So next row, 1s on the beginning and the end. Then you would add 1 and 3 to make a 4 here. Add 3 and 3 to make a 6 here. Add 1 and 3 to make a 4 here. And then go to the next row. And I'm going to just do a few more of these. So 1 here. 1 and 4 makes 5, 4 and 6 makes 10, 6 and 4 makes 10, 4 and 1 makes 5, and again, end with a 1. And 1, and then 1 and 5 is 6, 5 and 10 is 15, 10 and 10 makes 20, and we have 15 again, 6 again, and then 1. And then let's see, how many do I have here? 1, 2, 3, 4, 5, 6, 7. Let me just do one more because it's not that hard. Start with the 1, and then I got a 7 here. 6 and 15 is going to make 21, and then 15 and 20 makes 35, and then it's just going to repeat 35 and 21 again, and 7 again, and then a 1. So obviously there's space to continue this. I think this will be far enough for the purposes of what we're going to do here. But again, what we're going to use this for, and there are so many patterns that exist in this triangle, aside from just, adding to get the numbers to fill in here. But what we're going to see is a connection between these and the coefficients of our binomial expansions. So let's just look at our expansions really quickly. When we're expanding a plus b to the nth power, any binomial raised to a power, when I say expand it or binomial expansion, again, I'm just talking about multiplying out that binomial to by itself, however many times the power is telling me to do so. Now we're going to start with the power of 0. Anything raised to the power of 0 is 1, so a plus b to the 0 power wouldn't be any different. That would just produce a 1. And we know that anything to the first power would be itself, so a plus b to the first is just going to be a plus b. And then a plus b squared, this is something we've done plenty of. Let me just do the work on the side here. A plus b squared means we would multiply a plus b by itself. We're going to start with an a squared. And then we're going to have an ab here, another ab here, so that's two ab's in the middle. And then we're going to end with a b squared. And then if I want to cube that, a plus b cubed, then I would have to take an a plus b and multiply by an a plus b and an a plus b. Well, I just did that, so let me bring down my a squared plus 2ab plus b squared and multiply by another factor of a plus b. So I'm going to get an a cubed, and then I have a 2a squared b, and then an ab squared, and then an a squared b again, and then an 2ab squared, and then at the end here we're going to get a b cubed. So altogether I have an a cubed, and then I have 2 and 1 makes 3 a squared b's, and then 2 and 1 again makes 3 ab squareds, and then again this b cubed at the end. Now if I wanted to actually continue doing the multiplication, you can see just from the previous one that work gets a little bit tedious. So I took the liberty of expanding for you a plus b to the fourth and also a plus b to the fifth power. And what I would like to draw your attention to here are the coefficients of all of these terms in our expansions. So if I look here, I have obviously just a 1, but my coefficients here are 1 and 1. And my coefficients here are 1 and then 2 and then 1. So 1 and 2 and 1. And then here I've got a 1 and then a 3 and then a 3 and then a 1. 1 and 3 and 3 and 1. And then here, oopsie, okay, so 1 and then 4, 6, 4 and 1. And what we're seeing here is what we just saw in Pascal's triangle. So here's a 1, and then a 5, and then a 10, and then a 10, and then a 5, and then again a 1 at the end, where these numbers that I just highlighted, those are the same numbers we were looking at here. So the coefficients of my binomial expansions end up occurring in Pascal's triangle. So this would be what we would call row 1 of the triangle. Well, when n is equal to 0, our power n is equal to 0, we end up with just a 1. Or here we have row 2, and when we had n equals 1, we ended up with those coefficients of 1 and 1. And then in row 3, right, we see the 1, 2, and 1. That's what we see in the second power here. So that's what we saw when n was equal to 2. And so on all the way down. So we have n equals 0, then 1, then 2, then 3, then 4, then 5, then 6, and 7. So even though I didn't expand this out to the 7th power, I know that these would be the coefficients of an expansion of a plus b to the 7th power. Okay, so that's helpful. This triangle is giving me the coefficients of my expanded binomial. So my a plus b, or whatever my binomial is, to the nth power. Now, if there are other patterns existing, then this could make quick work of expanding a binomial, so or a product of binomials. And so let's talk about some of the other patterns. The one I just mentioned, it's a big one. The coefficients of a plus b to the nth power are in the nth rows of the triangle. Okay, so we saw that up here, right? We had our rows and our powers all corresponding there. And let me just get rid of this because they're really not as important as our powers. So power of 0, power of 1, power of 2. So when we count these, we have to just be sure that we start with a power of 0. Let me just make sure that this is aligned nicely. So this would be n equals 0, this would be n equals 1, then 2, then 3, then 4, then 5, then 6, and 7, and so on. And if you wanted to, later you could fill in some of those others. They might come in handy. And if you find yourself doing those expansions and you wanted to fill it in, then you have it for reference later. That's always kind of helpful too. But these aren't the only patterns that we see. We want again to make a quick work of our expansion. I don't want to actually have to multiply out something like a plus b to the 5th power. So what else is happening? Well, first, when we had the power of 0, we got 1 term. Power of 1, we got 2 terms. Power of 2, we got 3 terms. Power of 3, we got 4 terms. Power of 4, we got 5 terms. And power of 5, we got 6 terms. And it will always be the case that there are n plus 1 terms in the expansion of a plus b to the n. So whatever our power is, we'll have one more term than that power. Also, look at the first term in every single expansion, right, except for the 0 power. That's kind of a special one. But every term, I mean, it's actually the same, starts with a to the nth power. So in the a to the 0, I get a to the 0, which is just going to be 1. And then here, first power starts with a to the first. And here, second power starts with a to the second. And that happens all the way down. And so the first term contains a to the nth power. And then if we look at the last term, it's the same, but it's b to that nth power. So we start with an a to the nth, and we end with a b to the nth. So whatever this power is, we can apply that to the first and last terms. And then it's the stuff in the middle that kind of varies a little, but again, there's a pattern. So let's look at the power of a as we move successively through the terms. So let's look at the 5th, a to the 5th, or a plus b to the 5th. So the power of a starts at 5, that's what we just said, and then it's a to the fourth, and then it's a to the third, then it's a to the second, and then a to the first, and then a is gone. Well, technically it's a to the 0, but a to the 0 becomes 1, and that's why it disappears from that last term. And here it's 4, then 3, then 2, then 1, and then again it's gone. And then it's 3 here, then 2 here, then 1 here, and then it's gone. And so what we see happening with the powers of a is they are decreasing by 1 with each successive term. So the power of a increases, decreases. Why did I say increase? Decreases by 1 with each successive term. So we're starting with a to the nth power, and then we're going to decrease down by 1 with every single successive term until we end with our last term being a to the 0, a going away basically. And then b is working in reverse. If we look at the powers of b, we end with that b to the nth, and then, oh, that's a typo. And I did not catch this. This should be a 5 here for sure. So we start with a 5, and then we got b to the fourth, and then the third, and then the second, and then the first, and then it zeroes out in that first term. So the power of a is decreasing, but the power of b is increasing. So b starts at 0, and then it's 1, 2, 3, 4, and ends at 5. So they're working in opposites there. And let me just fix this again. My apologies for the typo, but that should definitely be b to the fifth. Okay, so the power of b, while a is decreasing, the power of b increases by 1 with each successive term. And then if we look collectively at the exponents within each term, so we have total exponents of 5 here. Here we have the 4 a's and then 1 b, which is 5 total. 3 a's and 2 b's, which is 5 total. 2 a's and 3 b's, which is 5 total. 1 a and 4 b's, which is 5 total. And then b to the fifth again, 5 total. And that's going to happen every single time. So we have the sum of the exponents in any one term equal to n. So if we're looking at a power of 5, the exponents in every term should add up to 5. So that means the degree of each term should be 5. Now there are several other patterns, but I think these alone are enough for us to do an expansion. So if I wanted to expand a plus b to the 6th powers, I stopped my list at a plus b to the 5th, but what is a plus b to the 6th going to look like? So first, I'm going to go to n equals 6 in my triangle and see what my coefficients are going to look like. So power of 6, that's going to be, let's see, 0, 1, 2, 3, 4, 5, 6, this one here, making sure I lined this up. So I know that these are going to be the coefficients in my expansion. 1, 6, 15, 20, 15, 6, and 1. And you see the symmetry in those, right? So I'm going to bring that down here. I know my coefficients are going to be, I'm just going to list them out. It was 1, 6, 15, 20, 15, 6, and 1. Just make sure I did that right. Yep. Okay, so I know these are going to be my coefficients. All right, so when I expand this out, actually, come on, highlighter. Right, straight from my triangle. So when I expand this out, I know I'm going to start with a coefficient of 1, and because I have an a to the 6th power here, I'm going to start with an a to the 6th power. And then b should start, or shouldn't be in this term. I start with an a to the 6th, and then b technically is going to be to the 0. Plus my next term, my coefficient will be a 6, and then a to the 5th power, because that should decrease, and then I'm going to have b to the 1st power, because technically here was b to the 0. That term goes away. And then the next term, so I'm going to add on, should have a coefficient of 15, and then a should be to the 4th power, and then b should be to the 2nd power. So we're going to see a decreasing and b increasing. And then we're going to have 20 here with a to the 3rd and b to the 3rd. And then we're going to have our 15 again, this time with a to the 2nd and b to the 4th. And then we're going to have our 6 again with a to the 1st and b to the 5th. And then finally 1 b to the 5th. And we've done it. We have expanded a plus b to the 6th power without actually having to do any multiplication. Okay, so there's an expansion of a plus b to the 6th. And this will work for whatever power. Obviously, they get a little bit lengthy. But if we can find our coefficients in the triangle, And then remember the pattern of the exponents where the first exponent decreases and the second one increases. So we start with our power and then decrease down to 0, or we start with the second one to the power of 0 and then increase up to the power that we're looking for here. And there it is. Okay, we've expanded. Now, unfortunately, most of our binomials that we are actually expanding are not just a plus b to the nth power. Right? When we go to expand binomials, they look like this: 2x plus 1 and 4x minus 5, and there are other things happening. Now, I'm sticking to linear examples here, but any binomial to any power, we should be able to use these rules to expand. So, if I was going to expand 2x plus 1 to, let's say, the fourth power, like in example 2, if our binomial isn't in the a plus b to the nth format, I would still start by expanding that form. So I'm going to use Pascal's triangle and the patterns that we just talked about in those powers and those exponents to expand a plus b to whatever the power is I'm looking for. And then I'm going to make some substitutions. I'm going to replace a with the first term in the binomial in my example, and then replace b with the term in the second term of the binomial in my example. And then all we'll have left to do is simplify. So let me show you what I'm trying to explain, which I don't know if that sounds or makes a sense what I'm saying. So if I was asked to expand 2x plus 1 to the fourth power, what I would do is expand a plus b to the fourth power. So if I expanded a plus b to the fourth power, again, I really want to focus on what are the coefficients and what's happening with the exponents, okay? So when I expand this out, let me go to my fourth power triangle here. So when n is equal to 4, my coefficients are going to be 1, 4, 6, 4, 1. So let me bring those over. I'm going to have a 1, and then it's going to be a to the fourth and b to the 0. And then I'm going to have a 4, a to the third, and b to the first. And then a 6, a to the second, b to the second. And then a 4, a to the first, b to the third. And then a 1, b to the fourth. And I say those ones, and I really don't like to write them, so let me just get rid of that. So 1a to the fourth. There they are. The coefficients from Pascal's triangle and the patterns of the exponents, a decreasing and b increasing. And you can also double check that the sum of the exponents in each one of those terms does still add up to 4. Now that's a plus b to the fourth. Since I actually have to expand 2x plus 1 to the fourth, now what I'm going to do is replace a, and I meant my highlighter, I'm going to replace a in each of these terms with 2x, because that's what I have in the first position of my binomial. And then I'm going to replace b in each of these terms with 1, because that's what I have in that second position of my binomial. And that will leave me something to simplify, and that would be the expansion of 2x plus 1 to the fourth. So when I rewrite this, it's going to become, instead of a to the fourth, it becomes 2x to the fourth plus 4 times, again, 2x is going to be cubed, and then we're going to multiply by b to the first, so that would be 1 to the first. And then 6, instead of a, again, 2x squared, and then b is 1 squared. And then 4a becomes 2x, b becomes 1. And then finally, over here, 1 to the fourth. And now we simplify, and we'll have our expansion. So 2x to the fourth power is going to be, let's see, 2 to the fourth is 16, and then x to the fourth is obviously x to the fourth. So the first term is going to be 16x to the fourth. And then here, remember exponents before we multiply. So this is going to be an 8x cubed, and 8x cubed multiplied by 4. 8x cubed multiplied by 4. And I'm trying to hold too much in my head. This is 8x cubed multiplied by 4 is going to make 32x cubed. And since this is just a 1, I don't have to worry about that. And then 2x squared is going to give us 4x squared. And then it has to be multiplied by 6. So I'm going to get a 24x squared here. And then in the next one, 4 times 2x times 1, that's just going to be 8x. And then in the last one, 1 to the fourth is just going to be 1. And so if I actually multiplied out 2x plus 1 by itself 4 times, this is the result. And to me, that is faster than actually having to do that multiplication.
but I have also done a lot with binomial expansion, so I find this useful. Maybe for some of the smaller powers, not super useful. It's because it's not really like that hard to square something. But for the cubic one, that's probably the one I use the most, and the fourth power one is helpful as well. When you go to calculus, you actually do a lot of expanding of binomial products when you find limits and you use the difference quotient. And you have to do something like x plus h to the third power. It's really nice to just know those rules and not have to multiply that binomial by itself 3 times. Okay? So let's try this again. Again, if I want to expand 4x minus y to the fifth power, the first thing I would actually expand is a plus b to the fifth power. And we actually expanded that one already on the front, but just so we can see it again, go to Pascal's triangle. My n equals 5. That's going to be here for my coefficients 1, 5, 10, 10, 5, 1. So 1, 5, 10, 10, 5, 1. So I have 1, a to the fifth. I always start with the a to the fifth, plus 5, and then it's a to the fourth, b to the first, and then 10, a to the third, b to the second, and then 10 again, a to the second, b to the third, and then 5 again, a to the first, b to the fourth, and then end with 1, b to the fifth. So there's a plus b to the fifth power, and now I'm going to, and again, just to, because this is a power of 5, that's why I expanded a plus b to the fifth. Now, I'm going to replace a in each of those terms with 4x, and I'm going to replace, I need another color, b in each of these terms with a negative y. So I want to make sure not to lose my negative. That will be attached to that y. And so this becomes, instead of a to the fifth, 4x to the fifth, plus 5 times 4x to the fourth times b, which is a negative y, and then 10 times 4x cubed times a negative y squared, and then 10 times 4x squared and a negative y cubed, and then 5 times a 4x and a negative y to the fourth, and then finally a negative y to the fifth. And now, cleanup time. Okay, now we actually have to simplify all this mess out. So, 4x to the fifth, well, we have 4 to the fifth and x to the fifth. Let's see, 4 times 4 is 16, times 4 is 64, and yeah, it's 4 to the fifth. Let me just use my calculator. 4 to the fifth power, 1024. So we're going to get 1024 x to the fifth for that first term. And then in this one, I have 5 times 4 to the fourth. I believe that's 256. But let me just double check. Yep, so 4 to the fourth, which is 256, and this will be x to the fourth, and then I still have to multiply by a negative y. So 256 times 5 is going to give me 1,280, and then I'm multiplying by a negative y, so it becomes a negative, I already forgot, 1,280, go back to red, negative 1,280, and then we have an x to the fourth and a y in that product. And in general, this will happen. You see how the first term was positive, the next one's negative. The signs are just going to alternate. When you have a negative in between, the signs will alternate. Okay, that's going to happen. And it should make sense as you work through this. So let's look at the next one here. We have 4 cubed and x cubed. So this will be 10 times 4 cubed is 64, and that's x cubed. And now the negative y being squared is going to make a positive y squared. So again, the sign's going to alternate. It's going to become a positive this time. So this will be a plus. 10 times 64 is 640. And then you have an x cubed and a y squared. And then over here, let's see, this is going to be 10 times 4 squared is 16, and that's an x squared. A negative y cubed will still be a negative y. So this one's going to be a negative. 10 times 16 is 160, x squared y. And then over here, 5 times 4x, can't do much with that, but the negative y to the fourth becomes a positive y to the fourth. So 5 times 4 is going to be 20, so positive 20, and then again an x and a y to the fourth. And then lastly, we have negative y to the fifth power, which will just be negative y to the fifth power. And there it is. that is the expansion of 4x minus y to the fifth power. Okay, so not necessarily difficult work, but you do have to be, careful with your signs and your calculations there. But in any case, I still think this would be easier than actually multiplying out these binomials by themselves 5 times. And you maybe disagree. Maybe you want to take the longer path, but yeah, it's an option, okay? So there are a couple of other options I want to show you. There's actually another pretty useful pattern. I credit one of my high school teachers for showing me this because I don't know that I've seen it, and I haven't really searched, so maybe it's on the web somewhere. But another useful pattern. So if I am expanding, if I don't have Pascal's triangle handy, like I have it sitting here in the notes, it's not that hard to use it. But if I don't have that handy, I don't necessarily want to build Pascal's triangle if I want to, let's say, expand something to the ninth power. I don't want to do all those rows to figure out what my coefficients are going to be, especially if there's another way to get them. And so there is, again, another useful pattern. If we multiply the coefficient and leading exponent of a term, and then divide that product by the term number that we are looking at, it will tell us what the next coefficient is going to be. So let's expand a plus b to the seventh, and I will try to show you how this works. So I know already that this is going to begin with an a to the seventh, right? We start with our a to our seventh power. And then the next coefficient, and maybe you've seen this pattern in here too, right? The next coefficient, when it's a power of 2, the next coefficient's a 2. Power of 3, next coefficient's a 3. Power of 4, next coefficient is a 4. But even if you didn't, here's what I'm going to show you for this new pattern. If I multiply my coefficient and my leading exponent, in this case their only exponent, and then divide by my term number, I will get the next coefficient. So what I'm saying to multiply is my coefficient of 1 and my exponent of 7. So 1 times 7 is 7. And then I divide by the term number. This is the first term, so the term number would be 1. So 1 times 7 is 7 divided by 1 is still 7. So I know my next coefficient is going to be a 7. And that was pretty evident in the triangle as well. So I'm going to have a 7 here. And I know that a to the sixth is going to be there, and I know that b to the first will be there. Now, to get the next coefficient without having to go to the triangle, I'm going to multiply 6 and 7. That's my coefficient and my leading exponent to get 42. And that 42 gets divided by 2 now because this is the second term. So 42 divided by 2 is 21. That is my next coefficient. And then a to the fifth and b to the second. And now multiply 21 and 5. That's going to get me 105. Divide by 3 because we're in the third term, and I get 35 for my next coefficient. So 35, a to the fourth and b to the third. And then multiply 35 and 4, that would be 120, 140, and divide by, oh man, I don't want to mess up my math. 35 times 4. Oh, look, I can I can math. And then I'm going to divide by 4 because it's my fourth term. That's going to take me back to 35. And now I don't have to do that work anymore. This will be a to the third, b to the fourth, because we have symmetry in this triangle, right? Once I get to the halfway point, right, or my numbers start to repeat, then I know I'm going to have the same thing over here that I had over here and vice versa. So now I know that after 35 I'm going to have a 21 again, and then a should be to the power of 2, and then b to the fifth, and then I'll have a 7 again, a to the first, and b to the sixth, and then I will end with my 1, b to the seventh. And there's your expansion without even having to go to the triangle. Okay, so kind of a cool thing. And then there's another option. Like, why not give you 3 or 4 options for something that you've probably never seen before? Okay, so the other option is actually a formula. So this is called the binomial theorem. It's used to find terms in your binomial expansion, again, without having to necessarily use any patterns, although I still think the patterns are easier. According to the theorem, the rth term, like nth term, but we can't use n because n is here. So we're going to call this the rth term of the a plus b to the n expansion is given by this. So this is a formula that we call the binomial theorem. That formula we can use to find any term in an expansion. Now we can technically, since we can find any term, I could find all of the terms in an expansion, but using the formula like 8 times is not nearly as efficient as just using a pattern or using Pascal's triangle. But if all we're asked to do is find one term in the expansion, which sometimes we are, like in example 5 here, just find the ninth term in the expansion, then maybe this formula is more useful than having to expand the whole thing and then say, okay, here's my ninth term. So this is particularly helpful for finding specific terms in an expansion. All right, so formula says that the rth term of a plus b to the nth power is given by our formula. So the formula says a couple of things. N and then r minus 1. This is weird. Hold on. N and then r minus 1 in the parentheses here. This is a weird thing. I don't know if you are familiar with that notation or have ever seen this before. And then n minus r plus 1, and then we're going to multiply by b to the r minus 1. So that's what the formula says. If I can identify all the components, that would be half the battle. The other half the battle would be just getting this into the calculator. So let's go to our formula, back up here again to our formula. So the n that's here is the power that we're looking for here. So in my problem, I know that n is, let me change colors. Sorry about that. Okay, so I know that n is going to be 11 because that's the power of my expansion. And then r, which shows up in a few places, r is the term number we're looking for. So the r that we see here, and then again a couple other places, again that is the r that we see here, that's the term number we're looking for. So if I'm looking for the ninth term here, I'm going to say r is 9. And then I need a couple of other things. I need to know a and b, but that's easy. We just saw that one there. These are the bases of my, sorry, my highlighter. Go to the y. The y. Okay, so a and b that we see here, these bases of these powers, these are just the terms in my binomial. So the terms in my binomial here being 3x and negative 2y. Just make sure that that negative is attached to that 2y. So we're going to say a is 3x, and we're going to say b is negative 2y. So according to this formula, I can use my calculator and find the ninth term of this expansion with this. So n is 11, and then r minus 1 would be 9 minus 1. And then we're going to multiply by a, which is 3x, and that's going to get raised to the n minus r plus 1 power. So 11 minus 9 plus 1, and then b is a negative 2y, and that gets raised to the r minus 1 power, so 9 minus 1. Okay? So actually, this part of it shouldn't be too bad. We know how to deal with exponents and multiplication. It's this thing over here that's strange. So this is notation for a number of combinations when you're choosing r items from a group of n items. Another common notation for this, I need another color. Another common notation for this is NCR. Again, number of combinations when you're choosing r items from a group of n items. Ultimately, all you need to know is it's a feature of the calculator. If you go into Desmos and you scroll all the way to the bottom, you will see that NCR button. And I have to put this in again because I'm a goof. Alright, so NCR. And what you're going to put in the NCR is the top number, and then a comma, and then the bottom number. So NCR in Desmos, and then it's going to give you the parentheses, and what you're going to want to put in the parentheses is the n and then the r minus 1 like this, and it's going to give you the calculation. So in this case, we're going to put in 11, and then we're going to put a comma, and then the 9 minus 1, which is just 8, so I'm going to put an 8 there, and so this thing has a value of 165, okay? And then that is going to have to be multiplied by 3x to the 11 minus 9 is 2, and 2 plus 1 is 3, so to the third power. And then we have this negative 2y to the 9 minus 1 is the eighth power. And now we're almost there. And I'm going to run out of space. So let's see. 165, I had 3 to the... I don't need a calculator for 3 to the third power. Just try to go in another color. So this is going to be 165 times 3x cubed. So 3 cubed is 27, and then x cubed, obviously x cubed. And then negative 2 to the 8th. Maybe I want a calculator for that. 2, not divided, raised to the 8th power is going to be 256. Well, negative 2 to the 8th power would still be 256. So this would be a positive 256 y to the 8th here. And then just one more time, now I can actually multiply all this out. So I'm looking at 165 multiplied by 27 multiplied by 256, and that's ginormous. What do I feel like? Yeah, yep, okay. So that is 1,140,480. And then we have an x cubed and y to the 8th power. So if I actually expanded out this product, if I multiplied 3x minus 2y by itself 11 times, then the ninth term of that expansion would be that ridiculousness that we just got there. Okay? Now, you don't have to use this formula. If I was going to do this without using the formula, I know that there's symmetry in my terms, so finding the ninth term would be a lot like finding the third term. So working backwards, right? We'd have 11, then 10, then 9. So think about this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and actually there's going to be 12 terms. So 1, 2, 3, 4 there. 1, 2, 3. So it'd be like finding the fourth term, finding the ninth term. There's going to be that symmetry. The coefficients in the a plus b to the nth power would be the same. You just got to flip-flop the exponents, and then you substitute in your 3x and negative 2y. And so you can still find this using the other patterns. It's just kind of a cool formula. I thought I'd introduce it to you so that you're not seeing it for the first time somewhere else. The weird thing is this. I hate to sort of just throw something random in here because we haven't talked anything about probability and combinations, but ultimately it's just something you got to put into your calculator. So hopefully you've got enough tools now to expand a binomial. You've got lots of options. You can find terms in the expansions. But if you find yourself needing some extra help, then just reach out. Until next time, take care.